Hello everyone. Hello students. I am Miss Amruta Jadhav ma'am, and today we are with the last part which deals with wave optics, in which all the theoretical part is going to cover in today's lecture itself. So here is the last part in which we are going to deal with the concepts which are related to resolving power. We already have seen what is resolving power, what is limit of resolution, that all we have seen. But in case of optical instrument, what exactly resolving power is, that we are going to deal in today's lecture. So let's wait, not to waste time. We are moving forward to the lecture. First, as we always do, we are going to revise what we have done in yesterday's lecture. Right? What we have done in yesterday's lecture? Yes. The first point is resolving power. What is resolving power? Do you remember what is resolving power? The ability to distinguish two physically separated objects as two distinct objects is nothing but resolving power of any optical instrument also. When we are able to distinguish the two physically separated objects as two different objects, then that is nothing but resolving power. We have seen the example of eye test also, in which the resolving power of eye will be changing from person to person. Okay, so this is all about resolving power. And the another definition of resolving power is it is reciprocal of limit of resolution. Right? So this is resolving power. Then next one, sorry for this. Next one is limit of resolution. What exactly limit of resolution is? As we can see the object which is in front of us, it is been visualized to us or visible to us by some angle. The rays which will falling on our retina, then we are able to see that object. And the angle or the minimum angle by which we can see that object or that resolved object is nothing but limit of resolution, and the reciprocal of that is nothing but resolving power, that we have seen already. Rayleigh's criteria that we have discussed yesterday. Rayleigh's criteria for limit of resolution, it deals with the concept of limit of resolution itself. As it deals with limit of resolution, obviously it will deal with the resolving power. What exactly the Rayleigh's criteria was? Rayleigh was the scientist who discovered or gives the idea about resolution, or he has given the idea about the object which are resolved, the object which are just about to resolve. He gives the idea about that graphically, and also by the laser beam also. We have seen the Aries disk, Aries ring, we have seen in yesterday's lecture. So according to this, two objects are just resolved when the first minimum of the diffraction pattern of one of the source coincide with central maximum of the other source. You have to just remember this. According to Rayleigh's criteria, just resolve means what? The first minimum of one source is coinciding with central maximum of another source. This is nothing but just resolve. They are visually separated. We can recognize that they are separated. So this is nothing but just resolve. And what is meaning of well resolved? They are completely separated and they are distinct from each other. So this is nothing but Rayleigh's criteria. So these all points we have discussed. Okay, so what now we are going to discuss in today's lecture? So as we have seen all about resolving power, then what next? So here is the answer. What is next? The point to be covered are resolving power of microscope, telescope and radioscope. Not exactly radioscope, but we are going to deal with microscope and telescope. The third point which we'll discuss, but it is very easy as compared to microscope and telescope. Okay, so this we are going to learn in today's lecture. For this, you have to go through the previous video which deals with the concept of resolving power. If you come to know what exactly resolving power and limit of resolution is, then only you will come to know what is that for the microscope, for the telescope, etc. Okay, so I hope you have gone through the video. So let's move towards our first point, which is resolving power of microscope. Here you can see the diagram in which we are supposed to consider AB as an objective. Now what is objective? You must have seen the not telescope, you have seen the microscope in our physics lab or in our biology lab. What exactly microscope is? It has the objective which we can move, and it has a lens inside it, so we can focus like camera, and by focusing that we can see the objects which are there in front of it or besides it. We can see that objects through microscope. So we are going to consider that microscope. Imagine that microscope is there and AB is an objective. Okay, O dash and O are the two objects separated by a distance A. The distance between them is A. Some concept you have to remember and you have to write when you are writing an answer. When you are going to draw a diagram plus description of the diagram will give you the total marks. Alright, so not just draw the diagram, you have to write the exact construction and information about the diagram also. So this is about O and O dash are the two objects separated by distance A of an objective which is in front of the objective AB. This AB is an objective of microscope. Now what is the medium between objective and that object? It has the refractive index n. We are going to consider it has the refractive index n. This. Okay, wavelength of light which is emitted by the source in the medium is lambda n, because inside a medium which is having refractive index n, the wave is traveling or the light is traveling, so we are going to consider this as lambda n. Okay, now the angular separation. What is meaning of angular separation? That we have seen in yesterday's or previous lecture. The separation here, this, the angular separation. When we are going to visualize any object, the angle which is created at this here is nothing but angular separation, and in this it is 2 alpha. As the angle is there, so we have written alpha. This is 2 alpha. These are the points which are very important, so I have underlined them. Now I and I dash are center of diffracting patterns. This I and I dash, and I is the first dark point of this all diffracting pattern. Alright, and Aries disk and ring due to O and O dash. We are going to find out Aries disk that we have seen on the screen. Okay, according to Rayleigh's criteria, the first dark that I just told you, first dark ring due to O dash, due to this point, due to O dash should coincide with I, and that of O should coincide with O dash, sorry, I dash. So O dash will be coinciding with I and O will be coinciding with I dash. Okay, then what exactly happens? Let's see in the previous next one. Here, see, the diagram is maximized over here. This is O dash. As in this diagram, O dash is very nearer to each other. Actually they are nearer to each other, but to study in geometric, so we have put in another diagram over here, which is O dash, which is, yes, sources, then A and B. Here A and B, here is the objective, that objective. Then when O dash comes to O will also comes to A. When O dash goes to B, O will also goes to B. So these are the ray when moving towards A and B. Okay, so we have drawn perpendicular to both of the lines, to the ray which is going towards B and to the ray which is going towards A. So first perpendicular which is OC, which is for O dash B. Second is OD, which is to O dash A. Okay, so these are the two perpendiculars. Now The nature of illumination at the point on the screen is decided by effective path difference. Obviously, that we have seen. When it forms a constructive, it will give you bright. When it forms a destructive, it will give you dark. So that is being decided by the path difference between them. So let us consider I, where the first dark ring due to O dash is located. See, we are going to consider I is a point where first dark ring is to prepared and path of the extreme rays reaching I from O dash. What will be that? What will be the path to be created from O dash to I? That will be O dash A and I. This O dash A and I in this way. O dash A and that will be I. Okay, and from B it will be O dash B I, O dash B and I. So this will be the path which is being created. As point I, it's symmetric with respect to O. You can see over here, it is very symmetric with O. The paths AI and BI will be equal. Why? Because O is symmetric with I. So this AI and BI will be equal. Thus the actual path difference will be what? What will be the actual path difference? It will be O dash B minus O dash A. O dash B minus O dash A. Why is it so? Because I is symmetric with O, so the path difference will be 0. That means paths are same, so path difference will be 0. So we are going to consider in case of O dash itself. So here is the path difference, which is O dash B minus O dash A. Okay, now according to this diagram, have a look at this diagram. What will be DO dash plus O dash C? What will be that? Have a look in the diagram and you will come to know what exactly it is. As the previous diagram is about microscope itself, but to give the exact idea about it, we have maximized that diagram, and in that diagram the region around O dash and O is enlarged, and from this figure path difference is nothing but DO dash plus O dash C. This will be the path difference. Alright, and that is nothing but twice A sine alpha, which is nothing but twice A sine alpha. So this is all about for microscope. Now when we consider a non-luminous object and when we consider a point object, what exactly happens to the resolving power, that we are going to see. Okay, here microscope with a pair of non-luminous objects which are dark objects. So now what is meaning of non-luminous object? Actually luminous or self-luminous objects are not observed because they are been illuminated by the external source, and then they get the light and then they get the luminous. So the non-luminous objects are illuminated by some external source. In general, this illumination is not normal. This is actually oblique. Okay, and the majority of the object viewed through the microscope can be considered to be point objects. Now considering Airy's disk, see, majority of the object viewed through the microscope can be considered to be a point object producing Airy's ring in their diffracting pattern. How the Airy's rings were formed, we have seen in previous lecture that red color laser beam has been passed through aperture and it gives you a rings that we have seen. Let the wavelength of light in this material be lambda n, which is nothing but lambda divided by n. What is that? Here lambda n is lambda by n. Lambda is being the wavelength of light in air and n is the refractive index of the medium. In such a setup, the path difference at the first dark will be what? Lambda n. So why is it so? As it is a dark point. we have considered that point is dark, that is the first dark point that we have said from the very first. So as it is dark, so it should be multiple of lambda itself. So here 2a sine alpha, which is the path difference that we have seen in previous slide, that is 2a sine alpha is equal to lambda n, which is nothing but lambda upon n. So a will be, by shuffling all the terms, a will be nothing but lambda divided by 2n sine alpha. This is a, and that term, that is 2n sine alpha, is nothing but a term which is known as 2, as 2 is constant, so we are going to separate out 2 and n sine alpha, and that n sine alpha is called as numerical aperture. That term is known as numerical aperture, which is that n sine alpha, and the resolving power a is nothing but inverse of limit of resolution, so you can take a inverse or reciprocal 1 by a, then it will be reverse, so you are getting twice Na divided by lambda. So this is resolving power for a microscope. Okay, when a point object is been considered. Now when self luminous point is considered, what happens to it? What will happen to it? We have to consider the Airy's ring over there here. By applying Abbe's theory of Airy's disk and ring to the Fraunhofer diffraction due to pair of self-luminous point, as we have considered as the heading is of self-luminous point. That means they are selfly illuminated the light and they are not being externally applied light over there. So for that purpose, the path difference between extreme rays at the dark ring is given by, directly you have the value over here, you don't need to prove anything. So that wavelength is given as 1.22 lambda. Path difference for that, when self-luminous point is considered, path difference is 1.22 lambda. Now for the requirement of just resolution, what is the requirement? This path difference should be this. So 2a sine alpha, as it is a path difference, should be equal to 1.22 lambda. So by shuffling all, we have got this equation. A is equal to 1.22 lambda divided by a sine alpha. Okay, so this is all about for microscope. Okay, so now let's move towards resolving power of a telescope. Have you seen telescope in anywhere? If not, then let me tell you, telescopes are the normally used to see the distant stars, and these stars are like luminous object for us, and they are very far off, and the diffraction patterns are like Airy's disk only. So the objects to be seen are far off, only the angular separation will be in consideration, not the linear separation. We are going to consider only angular separation, not linear separation. Alright, now the objective is AB that we are going to consider for telescope, and receiving two sets of parallel beams from two distant objects with angular separation theta. Here these are the rays which incident on this objective, and they are producing angular separation as theta. Okay, so the resolving power for that is defined as, resolving power of a telescope is then defined as the reciprocal of the least angular separation between the objects that are just resolved. Okay, this is very easy. Resolving power of telescope is defined as reciprocal of least angular separation. You have to write all these things. Reciprocal of what? Least is very important word. Least angular separation between two objects that are just resolved. These 3 points are very important in this definition, so I have underlined them. Alright, now According to Rayleigh's criteria, the minimum separation between the images I and I dash must be equal to the radius of Airy's disk. According to Rayleigh's, we have seen Rayleigh's criteria for Airy's disk also. So, if Airy's theory is applied to Fraunhofer diffraction, a pair of point object, considering that the first dark ring is given by here at 1.22 lambda, as just right now we have seen, when we consider two concepts together, that is Fraunhofer and Airy's disk, that the path difference is 1.22 lambda. Now for this, what will be path difference? B I dash minus A I dash, obviously. Here B I dash minus A I dash will be the path difference, path cover to go towards I dash. So that is 1.22 lambda. Okay, so this is the term which we are getting from that. And according to this, theta is 1.22 lambda upon d, or r is equal to d divided by 1.22 lambda. So that is what we are getting. Now where the d came from? If d is the aperture of telescope or diameter of AB, that should be multiplied to the angular separation, that is to theta. So we are getting d over there. Okay, so this is all about resolving power of telescope. Now how to increase that? This is the very important and interesting question. How we can increase the resolving power of telescope? As we have seen, what is the formula for that? It is d divided by 1.22 lambda. So we can say that resolving power can increase when diameter of the objective get increased, that we can say. But what exactly objective has? It has the lens. So diameter of the lens should be increased. This is the exact statement to increase the resolving power. But does it this possible? Because if we use a large lens, it will be very difficult to handle it. It will be having very heavy mass. So it will not be very easy to say that, or it is not the good solution for increasing the resolving power, that diameter should increase. Then what is the another solution for this? Is we can decrease the wavelength, as you can say from the you can see from the formula over there, which is r is equal to d divided by 1.22 lambda. So lambda is in the denominator, so you can directly say that they are resolving power of telescope and wavelength are inversely proportional. So when the wavelength goes on increases, resolving power goes on decreases, and vice versa. So they are inversely proportional. So this can be happen, but the solution for this has been done for the recent telescopes is segmented mirrors they have used for the telescopes. Here you can see, or parabolic mirror is being used to eliminate that. So these are the points which we can consider for how to increase the resolving power of telescope. Okay, this question can be asked in board exam for 2 marks itself. Okay, so let's move towards the next, which is radio telescope. What exactly radio telescope is? As we listen to radio, we listen to many radio stations right now. What exactly radio waves does? Actually, radio waves wavelength of that radio waves are in meters, and according to the equation which we have seen for the limit of resolution, that should be very large. The diameter of the radio telescope should be very large. Diameter of telescope means diameter of the aperture which is being used. So that should be very large. Very large means what? It should be in some kilometers. Obviously, a single disc of such large diameter is very impracticable. So these are not found to be nearer to us. So in this case, the antenna spreads over several kilometers, which is being used, and in Pune it is near Narayangaon, which is giant meter wave radio telescope. And we all, that is Maharashtrians, we used to find out the radio waves, and which has higher angular resolution, and it consisting of that GMRT, which is near to Pune at Narayangaon, which is consisting of 30 dishes of 45-meter diameter each, and which spreads over 25 kilometers, and it is the largest distance. And here you can see the picture in which 5 dish you can see over here. Photograph of 5 GMRT dishes is shown over here. Okay, the highest angular resolution is from about 60 arc second. Now what is arc second? It is arc sec is 3600th part of degree. 3600th part of a degree, very high. At the lowest frequency it is 50 megahertz, and it is to about 2 arc secs at 1.2 gigahertz. So this is nothing but for radio telescope. So these are the points which we have covered in today's lecture, which is resolving power of microscope, of telescope and radioscope, or radio telescope, which we can see. So I hope you understood all the concepts which are related to resolving power, and with related to microscope, telescope and radio telescope also, which is combinedly called as radioscope. Okay, so in this way I am declaring that wave optics chapter is being finished. This is the last lecture for wave optics, and from onwards we are going to deal with the numericals which are there for the wave optics. Okay, so please go through all the videos for the theory part, then only you will come to understand how the numericals can be solved. Thank you so much for watching all the video. Thank you all of you.